My name is Tom Delworth, and we're part of NOAA. I'm from a place called the Geophysical Fluid Dynamics Laboratory. And our mission here is to really build and use, especially models of the climate system. And our goal is improving understanding of the climate system on timescales from seasonal to multidecadal and longer. And we're looking both at the predictability of the system and the response to rate of forcing. We use observation and models, but our focus is really on building models to better understand the system. And we really have a focus, especially lately, on extreme events, because as we've heard so many times, those are pretty crucial. And they're interesting in terms of the dynamics of the system, but they're also where some of the largest impacts are. So we're very focused on those. So we try and take this basic understanding, which is always our goal, is to improve our understanding, and use that to develop and apply models. And the purpose of the models is really to translate that understanding to predictive capabilities of use to NOAA and society. So it's not a purely academic exercise. We're really trying to translate that understanding to models that can inform society across a wide range of time and space scales. And one of the challenges is that we're obviously in a changing climate. And so we're trying to deal with multiple factors simultaneously. We have just the inherent variability of the climate system indicated here, whether it's El Nino in the Pacific or other types of variability around the globe. We want to better understand the predictability of those various phenomena. How far out in advance can we predict them, to what skill level, and what observational requirements there are for that prediction. But those issues are bathed within this background of changing rate of forcing. And so what's the interplay between those modes of variability, predictability of the system, and how does the system respond purely to those changes in rate of forcing? So it's this complicated system which has a lot of different things going on. And we're trying to develop models that can tackle from all those different angles and bring them together in what we like to refer to as a seamless system. Many of you have seen something like this before, but for those who have not, we use models. And what are models? We break the globe, for example, up into a series of boxes. The faster the computer, the smaller those boxes are. Within each grid cell, we solve equations: conservation of momentum, mass energy, chemical reactions, rate of transfer, and we march forward in time by solving those equations, numerically approximating the solution of those equations at each time step to produce solutions going forward in time. This is the same paradigm used for daily weather prediction as it is used for centennial or longer scale climate change projections. And the confidence that we have in those models is built upon the confidence in the underlying physics, the numerics of the model. And those vary quite a bit. For example, this bottom right shows a snippet of some equations used in the model why the wind blows. Those represent conservation momentum. So a bunch of these equations solve all these grid points. And many of the models are becoming extremely comprehensive in terms of bringing in not just the physical climate system, but the biological aspects of the climate system, whether it's terrestrial vegetation, oceanic biogeochemical processes, and so forth. Those are all very important. So the models that we use are simply large computer programs that summarize our understanding of the Earth's climate system. And what I want to emphasize here is the size of these grid boxes is really, really important. As time has gone on and computers have gotten faster, we're able to use smaller and smaller grid boxes. And that really impacts the fidelity of the solutions that we generate from these simulations, especially with regard to extreme events. If we're using models that have a very, very coarse spatial resolution, it's really hard to have a prayer of representing some of the important dynamics that occur for those phenomena. As we go to smaller grid boxes, we have more of a chance. There's still a lot of uncertainty, but we increase our odds of doing that. So getting these small grid box sizes is really important. For us here at GFDL, we use a combination of models that we've built here in the laboratory. AM4 is the name for our atmospheric model. MOM6 is an ocean model that's used actually widely around the world, especially here in the US. And LM4 is the land model that we use in our framework. So we are doing something, we'll build a suite of models we call SPEAR. It stands for Seamless System for Predictions Earth System Research. So seamless in this context means that we go across all time scales, from predicting 1 or 2 months ahead to projecting 1 or 2 centuries ahead. We do this because we think there's a lot of value in doing that. And I'll articulate this more, but we use such models both for predictions of the climate system and long-term projections. Predictions, say a month or 2 or 3 ahead, we can evaluate from one perspective the fidelity of these models as prediction tools. And we think that gives us some insight into evaluating how much confidence we can have on longer term projections. So by putting our models to the test of doing real-time predictions, it gives us one insight into what we should think about them is for using in longer timescale projections. So we have here a suite of models that we use. Here are the names of these models. SPEAR is this acronym here. These show the resolutions of the various components, whether it's the atmosphere or the ocean. And these are the applications we use these models for. And in some sense, as we go down in this column, we're coming forward in time, because as computers get faster, we're able to reduce the grid size here. So we go to finer and finer resolution. So this row here we call SPEAR High 25 is the model that we're using now most commonly for projections of especially changes in extremes, because we're going down to what for global models is a relatively fine resolution, 25 kilometers by 25 kilometers, not quite the resolution of the observational precipitation data set we were looking at, but that's the ultimate target, obviously. And then we're actually going finer, and we have a model under development now with a 8-kilometer global ocean resolution. That's very important for a lot of oceanic processes, coastal processes, sea level rise, things like that. So we actually take our model components that we've developed here. These are building blocks that we combine into these various models we're using for both predictions and projections. So just to illustrate this point about predictions and projections a little more clearly here, because it's an important concept. So predictions are an initial value problem. That is what weather forecast models are. So we take the observed state of the system, we put those observations into a model with some adjustments to make the model behave well. We run that forward in time, and we get predictions, typically a season ahead or multiple years ahead in our decadal predictions. So that is like the weather forecast problem. We have an initial observed state, and then we predict how that state will evolve specifically ahead over time. Projections are a different beast. Those are boundary value problems. We're not trying to predict the year-to-year detailed changes or month-to-month changes. Rather, we give the model the overall changes or projected changes to atmospheric composition, aerosols, greenhouse gases, et cetera. We run those forward in time, and we get climate change projections. So to illustrate this, a prediction, it answers the question, how will tropical Pacific Ocean temperatures, El Nino, how will they evolve in the coming months? A specific prediction, say, for the coming winter. Projections answer the question, how do the statistics of Pacific Ocean temperatures change in response to, say, increase in greenhouse gases? So those are different problems, but we try to develop a system in which we do both of those problems coherently and seamlessly from seasonal to multidecadal timescales, because it's interplay across timescales. The same underlying physical processes or very similar processes are operating across timescales, and we can use these predictions as tests to gain a perspective on what we should think about the longer term projections of these models. If they're really, very poor at predictions, that gives us some pause, perhaps. So we can use these very carefully. Also, the fact that we use the same models, climate change, radiatively forced climate change, is changing the characteristics of shorter timescale predictions, and so we can assess that interplay using this very seamless framework. So just go a couple of examples of the kinds of things that we do across timescales. This is on the shorter timescale, the seasonal timescale. We do lots of real-time seasonal predictions, and we have been participating in something called the North American Multi-Model Ensemble. And this is the kind of skill we have in predicting, with 8-month lead now, atmospheric river activity, not individual atmospheric rivers, but the statistical characteristics of atmospheric river activity over a region. This is 8 months ahead. So these are predictions initialized in April for the following January through March. And these are verified from long sets of hindcasts. So we do have some skill in predicting 8 months ahead atmospheric river activity. Actually, this capability is now being transitioned to the National Weather Service for an operational tool. So when we then think of changes on longer timescales of atmospheric river activity, decade by decade ahead, we can at least gain some perspective. This model is capable of, with skill, predicting atmospheric river activity 8 months ahead. So some of the processes have some degree of similarity with reality. Not perfect by any means, but this is just one perspective on evaluating models. We also do things like new predictions of seasonal quantities like wind energy or solar energy. We have skillful predictions of how much wind energy will come a couple of months in advance in the wind producing areas of the country, or solar energy. So these are on the shorter time scales we're looking at. Again, both for the value of the predictions themselves, but also how they then translate and give us perspectives on the longer timescale capabilities. We also have a decadal prediction system that we use here at GFTL. And there on the decadal timescales, we are really looking to the ocean. For the ocean has very long timescales, very slow processes. And by trying to predict that, we can gain some insights on predictability of the climate system writ large, whether it's in the Atlantic or other basins. So on these decadal timescales, the variations are now a combination of natural variability and irradiatively forced climate change. And so we use these skill in ocean decadal predictions to in some sense evaluate or assess confidence in longer term ocean projections. Will the large scale flow in the ocean change dramatically? So that's very useful for us. For example, this sort of decadal scale ocean predictability can lead to multi-year skill on things that are quite important. So this is an example. We now have along these stations along the U.S. Northeast coast, we have skillful multi-year predictions of coastal flooding that are now possible. Actually, the paper coming out later this week in Science Advances looking at skillful multi-year predictions of coastal flooding events along the U.S. Northeast coast. So that's quite an important topic, I think. But also then when one looks at longer timescale projections of things like that, we're able to shine a light on the fact that the model is able to produce shorter timescale predictions. So it's very important for us to have that capability across timescales. And then we also go out to the longer timescales within the same modeling framework, looking at these climate change projections. So these are various, actually, you've seen in a couple of the talks already, some of these SSPs, that's shared socioeconomic pathways. They're estimates of future changes in atmospheric composition based on various assumptions. The red indicates a stronger rate of forcing. The x-axis here in calendar year and time out to year 2100. Y-axis is the carbon dioxide concentration in the atmosphere. This black line are the observed changes, and then these colored lines are various future assumptions. They're all over the place because we don't really know what the future will hold in terms of changing greenhouse gases. But we do many, many simulations using all of these potential future scenarios to gauge a better sense of the PDF of potential future climate change. Some of them are very aggressive. Some of these are heavily mitigated scenarios. Also scenarios I'll discuss briefly later in which CO2 goes up and then comes down, assuming some sort of emissions reduction policy goes into place. And we ask the question, how does the climate system recover? Do we simply revert to the climate state we were in 30 or 40 years ago, or are there nonlinearities that we have to? So we run very large ensembles of each of these, and we're really wanting to quantify the natural variability and to better characterize the probability of extreme events in this changing climate system. So we use these large ensembles using all of our models, many, many different cases, so hundreds probably of cases, and we have large scenarios, large ensembles to really better characterize the tails of those distributions, to really look at the extreme events. And we have the relevance is looking at the attribution of real-time seasonal scale prediction. So how much, when we do, for example, we do a seasonal prediction, when we look at the summer coming up ahead, we can estimate how much that is due to internal variability and how much is a response to changing rate of forcing. Here's an example of some work using these models. This is the observed trend in tropical cyclone density over the globe from 1980 to 2018. Red indicates increased cyclonic activity, blue reductions. These are the observations. Here are model-based projections of what that should have been, given the change in CO2 and aerosol. So not a perfect agreement, but a pretty good correspondence, showing that you can explain a good deal of the observed changes in tropical cyclone density from these changes in rate of forcing. We also use these to predict and project extreme heat and storms, regional hydroclimate change, extreme precip, ocean circulation and variability. We also would like these at least to be used for risk assessment and support of decision-making, as well as looking at the reversibility of climate change. One of the interesting things, for example, a study a few years ago looked at from a climatic modeling perspective, the day zero drought event in Southwest Africa, where they were about to run out of water in their reservoirs. And so you can then use these sorts of models to gain a perspective on how likely that is and how that's going to change in the future. So just a couple of last slides finishing up. So we're really focusing on extreme events. So this is from a paper a couple of years, 1 or 2 years ago, looking at extreme rainfall events over the northeast part of the United States. So this shows the quantitative value, millimeters per day, of the 99th percent threshold for fall daily precipitation. So this left panel is the observations. These blue colors indicate how much rainfall corresponds to 99th percentile. And then we look at how well models can do in simulating that. Can models simulate these extreme events? So if we look at first these right two models, again, the color indicates the value of precipitation at the 99th percentile, you can see that these are much paler. These are two models, one from here at GFDL, one from NCAR in Boulder, that are both of a much coarser resolution, 100-kilometer grid. They're too coarse to simulate the real dynamical processes giving rise to these extremes. They don't do very well. You move to the next model, it's 50 kilometers, because we're now a little bit better resolving some of these smaller scale processes we do better. But finally, we move over to something called Spear High 2025. We have, again, even smaller grids, 25 kilometers, and you get a much more realistic simulation of those extreme events. So by using these large ensembles of now high resolution models, relatively high resolution, we think they're better able at least to simulate some of the characteristics and mechanisms of changes in extreme precipitation. This right shows essentially that time series of extreme precipitation simulated in different models for Northeast US. Green is high resolution. This dashed line is medium resolution, and the dotted line are low resolution. So again, the same message that high resolution produces much more realistic simulation of extreme precipitation events. So we can then use that as one interesting case study looking at southeastern United States extreme precipitation. So this is a model-based study, hasn't been published yet, but we're looking at using our high-resolution models, large ensembles, how do extreme precipitation events change in the past and going forward using these relatively high-resolution, large ensemble predictions. So the y-axis here is the number of 100-year precipitation events over the whole region of the southeastern United States that are simulated each year. So for example, this black dot for this year looks like a value of about 300, because we have a lot of different grid points in the southeastern US. We have many different realizations. We have a very large number of events. We can simulate 100-year events with some statistical robustness within this modeling framework. So these black dots then go up in time as we go forward in time. We're using now what's called the SSP245 estimate of future change in atmosphere composition. That's a relatively middle of the road estimate. So what's interesting here is we go from this period of the 1990s, and now we're in the 2020s. If you look carefully at all these black dots, these are model-based simulations of how many once in 100-year events we would simulate over the Southeast US. There's no overlap between the 1990s and the 2020s, simply due to increasing greenhouse gases, changing rate of forcing in the system. We've gone to a different distribution of events. I was actually quite surprised that it was such a clean separation here in a model. So then we continue forward in time, and you can see these black dots continue going up as we increase the rate of forcing. We're also really interested in the question of reversibility of climate change. If you, at some point, put in place policies to reduce emissions, what happens? That's where these green dots, if in this case, in the year 2036, we start to reduce emissions and CO2 declines. And so you see these green dots then peaking and falling over. And in this scenario, a very idealized scenario of future reductions in emission, by the late 21st century, we again have totally separate distributions. The green dots are from a simulation. These are a number of 100-year events over the southeastern United States in this scenario with emissions reductions, and here's with unabated emissions. So very different. So we think there's at least interesting scientifically to gain a perspective on the possible changes in distributions going forward. So just final slide here. We are really keenly interested in looking at the predictability and the projections of regional extremes using these high resolution models, large ensembles to gain much better fidelity in terms of statistical distributions. And we're interested in things like from atmospheric rivers to heat to coastal sea level, lots of different things involved there. As one example, another further example of the impact of resolution, we had big Santa Ana wind events, last fall and actually last winter, and tremendous fires over Southern California. And so we're looking at how well our models are able to actually simulate Santa Ana wind events and how then much confidence one might have then in projecting their changes into the future. So on the top panel, this is an observed Santa Ana wind event. Goes from Los Angeles to Nevada. The black shows the outline of the topography, the mountains. And during the Santa Ana wind event, you get cold air building up in the interior, the Great Basin, Nevada area. That creates a strong pressure gradient between the interior and the warmer coastal regions, creating these strong flows that move from the interior to the coastal regions. These colored contours indicate temperature. So blue means cold temperatures, red, much warmer here near the coast because you have these strong winds and warming as they descend downhill. So this is the structure of a typical Santa Ana wind event. This is observations. The middle panel shows a simulation of these events using a coarse resolution model, 100-kilometer model. You can see the very, very smooth topography here. You can't really resolve these mountain chains. And all you get is this big blob of cold air. You don't get anything like the observations. If we then move to a 25-kilometer resolution model, so we get not perfect, but a better representation of the topography, which is giving rise to this flow. And we get this cold pooling in the interior and much warmer air in the coastal region. So by, again, moving to these high resolutions, we're better able to simulate some of the extreme events that matter so much to various aspects of infrastructure and society. So we're trying to push very hard on that. And so we're trying to connect these predictions and projections to societal impacts. And finally, we're really interested, I just alluded to this topic of climate reversibility. If we were to reduce emissions, do we simply reverse the climate change we have seen, or do some aspects prove more intractable to such reverse? And we do actually see some aspects of the climate system proving more intractable to changes in emissions, and particularly the role of the ocean comes into play very much there in terms of predicting changes, because the ocean, some aspects of the ocean circulation especially, can take very long time scales to adjust, and they'll persist long after emissions are reduced. So that's in a nutshell what we do, and some of our scientific interest in moving to these models. We try and improve our understanding and predict and project climate change out from one season ahead to a century ahead. So thanks very much.
All right, thanks, Tom. Questions for Tom?
Then I have a question to Tom. Thank you very much, Tom. This is very informative. There is big interest in the forensics or attribution, and I'd like maybe some comments from you. What's the role of these models in attribution and forensics after a major event?
Well, Joe Barsugli is on the line. I'm sure he'll have much more to say as well. But I think they play a role. They play an important role. They play because you can then run models after the case and see and dissect what the various factors are responsible for various events. For example, we actually do seasonal hurricane predictions, and some seasons are different than other seasons. So after the fact, in many cases, we'll rerun those simulations and probe the role of Atlantic sea surface temperature conditions, the role of El Nino, the role of aerosols. So they can be used very effectively to dissect, as you say, the causes of some events. The big caveat, though, of course, is that the models have to be able to robustly simulate the underlying causes of these events in order to be very useful. So because we test our models, for example, in the case of hurricanes, we do run them and use them as predictive tools, and we have skill in that prediction. So it gives us a little bit of confidence that these attributions have merit. But there are other features where, for example, this model or other models are far less skillful. And so doing attribution studies with models that aren't able to really simulate the underlying physics can be very problematic. It can be actually quite easy to do and to run such simulations, but we have to be very careful that that tool has to be really up to a proper representation of the physical processes in order to be really taken literally and faithfully as attribution statements. I don't know if Joe Barsugli wants to add any more to that.
Yeah, I heard my name there, but no, I agree with you. You always triangulate with the observations and the cause and effect that you get from the observational analysis to see whether it's not so much the actual value that you get out of a climate model, but primarily whether the relationship among the variables between SST, local ocean temperatures and local temperatures, for example, or whether you get the relationships are correct, then you really feel that the model is capturing something. As Tom said, I mean, you don't take them only at face value. You do, but it's not a simple thing to do, as he said. But for certain things like temperature increases, where you see very broad scale effects, certain things even like precipitation extremes, where you see it happening in many, certainly in the same direction and often in the same magnitude over very large areas, that you can, let's say, feel that the inaccuracies in the model itself are not going to affect the overall conclusions. So that's kind of how we go about it, I would say. Tom, wouldn't you? Wouldn't you say we apply a layer of inference on top of the models?
That's right. I actually briefly mentioned this case of Southwest Africa and Cape Town, and it's really fascinating to be able to look at that day zero event in the context of these high resolution models and understand how lucky or unlucky they were. For for various factors. And of course, then if within that context, and look at how things will evolve over the next few decades. And their picture doesn't look very bright, actually, in terms of water supplies over that region. But it is really a very important tool for attribution, as long as it has all the caveats of it's not an off-the-shelf product. And you really have to, most important thing actually is the human intellect that goes into interpreting these.
Dan?
Yeah. So I was interested that Bilal asked about the attribution work. Just as a note, one of the projects we funded a few years ago was trying to bring together different aspects of NOAA's capabilities, like GFDL's modeling and the work at PSL and series that Joe's involved in, and our capabilities in NCEI to do attribution work and explaining extremes work generally. It was, I think part of the theory of it was it gets to like similar sort of degree of understanding as just doing forward-looking projections, but it kind of inverts or changes the way that the information is received by communities that we work with to provide it to. And so I was curious why Bilal asked about attribution, because in the ASE relationship, we really have talked a lot about just the raw projection data, getting that into useful forms. What's your interest in attribution? What do you think your communities or engineering communities learn potentially from attribution studies that you maybe don't get, or that you get differently from just forward-looking projection information and integrating that into planning practices? I would love to hear why you were interested in that.
I mean, there is a publication that came out that was done by the Structural Engineering Institute, and they had a section or a chapter, I think, on attribution, and I did prepare the content for it. And I did collaborate with one of your young engineers. What's his name? He left GFTL recently.
Zach Labe.
I'm sorry?
Yes. Zach Labe.
Yeah, exactly.
Yeah,
right.
yeah.
We have a paper together with my postdoc, and I think the interest, I mean, the interest sometimes in terms of it could be for quantifying lack of actions. It could be for building the business case. I mean, I could see benefits of this time, that if I could identify events that are attributable, can be attributed to a changing climate, and it could offer a basis for justifying maybe more investment and more resources. The risk profile, it could become maybe a basis for not projection, but aggregation of what's the potential loss that we could have if those events that do not happen everywhere, and I could attribute some and basically project that they could happen elsewhere, just randomly they did not happen at this site or that location. So it could help in maybe building the business case. And the business case doesn't need to reach to the level of monetization, but it could bring the loss accumulation or loss assessment to that will become the basis for doing the economic valuation, feeding it into economic studies.
Yeah, I think like Eric's presentation kind of gets at that a little bit. He starts showing this photo of himself adjacent to the Hudson River with this washout event, which they then had to figure out a really clever way to engineer a solution for afterwards. And then, Eric goes on to like talk about this, set of meteorological analyses, really trying to think about this in a bulk manner and identifying, proactively a number of other structures that may be similarly vulnerable. And it's almost like, I feel like his talk kind of highlights these two modalities of operation, where you like have the event happen and then you have to come up with a solution that's in response to the event, but then you can connect that to like, let's be really proactive, as Eric was saying about the way in which we integrate meteorological information into other designs more broadly. I don't know. It's like, yeah, it's really great to hear you talk about it, Bilal. I think it's really interesting to get a practitioner's view on the value of attribution studies as opposed to just the forward-looking information.
If I can give a little example there from that work, we were looking at temperature extremes, and of course, daily maximum temperatures on average have not increased very much in most of the central and eastern US. And this is largely because there's been an increase in precipitation over the last 40 years. The causes of that precipitation increase are multiple, but when you look at it and start piecing it apart, then you can say, well, for the given amount of precipitation on the dry side, you get certain temperature extremes. We just haven't seen as many of those. But if we did see them, we have seen both in the models and in observations a similar progression to when it's precipitation deficit during the summer, you're getting 1 or 2 degrees Celsius warmer extremes on the high side. So a plane analysis shows no increase, but the conditional analysis on precipitation says when it does dry out, it's going to be hotter than things you've experienced in the past. So it identifies, we just call them latent risks, is conditionality. That's one thing that attribution can do, especially when there's a sort of a complex mix of factors there. And so that's what I wanted to get at. The attribution story is often a layer of, how do you want to put it? It kind of explains risks that you may not see on the surface that may come out. And that's why I think it's kind of important to include things like that.
Yeah, I absolutely endorse that, very strongly. I would also say that in addition, attribution studies, I think, are actually important in assessing the credibility of models that you use for your projections. If you are interested in certain phenomena and there's an event, and the models you're using for projections simply aren't able to simulate that, and so they're unable to do a credible attribution study, that has to inform one as to how much you use such models for your projections going forward. So there are multiple uses of these attribution studies.
I did add to the chat session. I didn't know that chat allows you to put a PDF, but I did put a PDF in there. I hope it can be received on the other end. That's the paper with Yating and Fung. He's at NIST and Levy.
My question is, we know that there's a little bit of an uncertainty around Atlas 15 Volume 2, but I guess my question is, obviously the advantage of Atlas 15 Volume 2 is it's a gridded product. It's would be very useful and somewhat obviously analogous to Atlas 14 and then Atlas 15 Volume 1. Has there been any thought given to comparing, like the kind of results that you would get out of SPEAR, which are obviously at a little bit coarser resolution, to using the kinds of adjustment factors based on the Clausius-Clapeyron relationship? I mean, has anybody done anything along those lines just to kind of get an idea of, are there significant differences that would be important to know, or is that just not within the scope of work?
We actually have provided some of our SPEAR projections of high frequency precipitation to Atlas 15. So I don't know what happened, what has gone on, but I think those sorts of comparisons are very, very useful, potentially.
All right, good. Thanks. We can pursue that.